Hi. To give insight into the structure of a group, we study a series of embedding subgroups of G. That means subgroup series can simplify the study of a group to the study of simpler subgroups and their relations. So in this session, we define subnormal series, normal series, composition series, and some examples. So first we see the definition of subnormal series. So what is a subnormal series? Let G be in a group. You take the chain of subgroups, begin with identity and end at G. See here in this, here you can see that it begins at E, which we call it as G naught, and which is contained in G1, contained in G2, etc., contained in Gk minus 1, which is contained in Gk, which is same as G. That means each Gi's are subgroup of G and Gi is contained in Gi plus 1. And this series of subgroups or a sequence of subgroups is said to be a subnormal series if each Gi is a normal subgroup of Gi plus 1. That means G naught is a normal subgroup of G1, G1 is a normal subgroup of G2, G2 is a normal subgroup of G3, and so on. Gk minus 1 is a normal subgroup of Gk, which is same as G. Then we can say that if we can have a finite sequence of this type, then we can say that that series is a subnormal series. Now if each Gi, that means G0, G1, G2, G3, etc., Gk minus 1, if all of them are normal in G, then we can say that this series is a normal series. So the normal series, in the normal series, all groups are normal subgroup of G, or all subgroups are normal subgroup of G. In a subnormal series, each subgroup is normal in the next immediate subgroups of G. That means Gi is normal in Gi plus 1. That means G0 is normal in G1, G1 is normal in G2, and so on. The length of a subnormal or a normal series is the number of proper inclusions. That means G0 is properly contained in G1, G1 is properly contained in G2, and so on. Gk minus 1 is properly contained in Gk, then the length of this subnormal series is k. We'll see some examples. You know that every subgroup of an abelian group is a normal subgroup. Therefore, any series of subgroup of an abelian group is a normal series. So, for example, if you consider integers, which is an abelian group, in fact it is an infinite cyclic group, and so it has infinitely many subgroups which are also cyclic. So if you start with a 5z, which is a subgroup of z, which contains the elements of the form 0, plus minus 5, plus minus 10, plus minus 15, etc., all multiples of 5, and 15z, which is contained in 5z, 45z is contained in 15z, and 0 is contained in 45z. So this is a series of subgroups of z. And because each subgroups are normal in z, because z is abelian, this one is a normal series. So if you consider a finite group, for example Z24, which is a cyclic group of order 24, and we consider the subgroups, which is again a cyclic subgroup, which is, suppose we consider the subgroup or cyclic subgroup generated by 2, that group contains how many elements? 12 elements, namely 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. These are the 12 elements of the cyclic group generated by 2, which contains the cyclic subgroup generated by 4, which contains the cyclic subgroup generated by 8, which contains the identity 1. This series is also a normal series because Z24 is an abelian group, and each subgroups are normal subgroup of this one, the group, therefore it is a normal series. In fact, every normal series is a subnormal series, because you know that if a subgroup is normal in a group itself, then if GI is normal in G, then definitely GI is normal in GI plus 1, because you can think of every element of GI plus 1 as an element of G. But the subnormal series need not be a normal series. That means if GI is normal in GI plus 1 for each I, that does not mean that each GI is normal in G. See, for example, if you consider D4, which is a dihedral group of out of 8 and is the group of symmetries of a square which contains 8 elements. And so which contains rotations, 4 rotations and 4 reflections. So if you consider the subgroup which contains only the reflections and identity, the identity 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. If I call it as H, then H is a subgroup of D4, which is G. So index of H in G is equal to 2. Therefore, H is a normal subgroup of D4. Because we know that any subgroup with index 2 is normal subgroup. If I call it as K is equal to identity and 1, 2, 3, 4, the second one, we call it as K. Then this is K and this is H. What is the index of H in G? Index of K in H is equal to 2. Therefore, K is normal in H. And this one is also, identity is clearly normal in K. So, identity contained in K, contained in H, which is contained in D4, this one is a subnormal series. But this one is not that means K is not a normal subgroup of D4. Why it is so? Because if you take 1, 2, 3 into 1, 2, 3, 4 into 1, 2, 3 inverse, that is never be equal to identity or 1, 2, 3, 4. Therefore, it never belongs to K. So, it is not a normal subgroup of D4. But that one is a normal series. Therefore, subnormal series. Therefore, every subnormal series may not be a normal series, but every normal series is a subnormal series. Now we will see the refinement of subnormal series and a normal series. Suppose you have a series H0 contained in H1, contained in etc., contained in Hn minus 1, which is contained in Hn, which is equal to G, where H0 is equal to identity. So suppose this series is a normal series or a subnormal series of G. And E is equal to G0 contained in G1 contained in G etc. Gk minus 1 contained in Gk, which is equal to G. That series of GIs is said to be a refinement of the series which includes HIs if each HI is one of the GI. That means that the refinement series contains each of the terms of the original series. That means in the refinement series more subgroups are included. See, for example, if you consider this normal series, the 0 which contained in 200 is Z, contained in 50 is Z, contained in 5 is Z, contained in Z. So the above one, this one, 0 contained in 200 is Z, contained in 100 is Z, contained in 50 is Z, contained in 10 is Z, contained in 5 is Z, contained in Z. This one is a refinement of this series. Because in the refinement series, 100 is there and 10 is there more. And each 200 is there in both the series, 50 is there in both the series, and 5 is also there in both the series. So therefore, the 0, 200 is 500 is 100 is 50 is 10 is 5 is which is contained in Z, which is a refinement of the series 0 contained in 200 is contained in 50 is contained in 5 is contained in Z. So to study about the subnormal series of a series G naught contained in G1 contained in GK minus 1 contained in GK, which is equal to G, we need to study the factor groups. We know that GI is normal in GI plus 1, therefore GI plus 1 mod GI is a quotient group which is defined. So therefore, if we want to study about the subnormal series, we need to study about the factor groups GI plus 1 mod GI. Now when can you say that there can be many subnormal series and normal series for a group G? When can you say that two normal series or two subnormal series are equivalent? Two subnormal series, one is in GIs and the other one is in HIs, are said to be equivalent if there is a one-to-one correspondence between the factor groups of GIs and the factor groups of HIs. That means if you consider the set GI plus 1 mod GI for I 0 less than or equal to I less than or equal to k minus 1, and if you consider the set of factor groups of HIs, namely Hj plus 1 mod Hj, where 0 less than or equal to j less than or equal to n minus 1, if we can find a 1-1 correspondence between these two sets, then we can say that the series which is defined by GIs and the series defined by HIs are equivalent. Now we'll see some example. So consider 0 contained in the cyclic group generated by 12, which is contained in the cyclic group generated by 4, which is contained in Z24. And another sequence or the series of subgroup of this one Z24 is 0 contained in the cyclic group generated by 6, which is contained in the cyclic group generated by 3, which is contained in Z24. Because Z24 is an abelian group, both these series are normal series. Both these series are equivalent. Why? Because we will find out the factor groups of the first series. The first series, the factor groups are the cyclic group generated by 12 mod 0. The cyclic group generated by 12, which contains only two elements, because namely they are 0 and 12. And so the quotient group 12 mod 0, the cyclic group generated by 12 mod 0, which is isomorphic to Z2, because this quotient group contains only two elements. What about the cyclic group generated by 4 mod the cyclic group generated by 12? This one, the 4 contains how many elements? There are 6 elements in this group and there are 2 elements in this group. So this quotient group contains 3 elements. Therefore, this quotient group is isomorphic to Z3. What about this? Z24 contains 24 elements and this contains 4 elements. Z24 mod 4 contains 4 elements, and we can see that one is isomorphic to Z4, because we know that there are two types of groups of 44 are there. One is the cyclic group and the other one is clean 4 group. Clean 4 group is Z2 cross Z2, but here we can easily show that Z24 mod 4 is isomorphic to Z4. But what about the other series? So here you can see that the cyclic subgroup generated by 6, which contains 4 elements, and 0, so this quotient group contains 4 elements. This one is definitely isomorphic to Z4 because it's a cyclic group. 6 is a cyclic group generated by 6. And 3, this subgroup, the cyclic subgroup generated by 3 contains 8 elements, and this 6 contains 4 elements, so the quotient group contains 2 elements, so it is isomorphic to Z2. And in Z24, which contains 24 elements, this 3 contains, the cyclic subgroup generated by 3 contains 8 elements, so this quotient contains 3 elements, so Z24 mod 3, the cyclic group generated by 3 is isomorphic to Z3. So you can see that Z2, there is a 1-1 correspondence here, Z3, and Z4, Z4. So there is a 1-1 correspondence between this set and this set. Therefore, both these series are equivalent. Now we will define what a composition series is. Suppose we have a sequence of subgroup Let G be a group, and we have a sequence of subgroup, begin with identity and end with a G. And there are G0, G1, G2, etc., Gk minus 1, where Gi is contained in Gi plus 1. And this sequence of subgroups is said to be a composition series of G if Gi is a proper normal subgroup of Gi plus 1. That means this series is a subnormal series and Gi plus 1 mod Gi is a symbol group. That means the factor group is a symbol group. That means that a sequence of subgroups is said to be a composition series if that series is a subnormal series and all factor groups are simple. So we have discussed about the symbol groups in the previous session. So we know that simple abelian group is actually a cyclic group of order P. So to check whether, for example, we see is that consider the group Z36. Consider the series 0 contained in the cyclic subgroup generated by 18 contained in cyclic subgroup generated by 6, which is contained in cyclic group generated by 2, which is contained in Z36. What are the factor groups? Z36 mod the cyclic group generated by 2, which contains 2 elements because Z36 contains 36 elements, and the cyclic subgroup generated by 2 contains 18 elements. So the quotient group contains 2 elements, so it is isomorphic to Z2. And Z2 is a symbol group because there is no proper normal subgroups. And the cyclic group generated by 2 mod is a cyclic group generated by 6. So the cyclic group generated by 2 contains 18 elements and the cyclic group generated by 6 contains 6 elements. So the quotient group contains 3 elements. So it is isomorphic to Z3 and Z3 is simple. And the cyclic subgroup, the quotient group of the cyclic group generated by 6 mod with the cyclic subgroup generated by 18. The cyclic subgroup generated by 6 contains 6 elements and the cyclic subgroup generated by 18 contains 2 elements. So the quotient group contains 3 elements, so it is isomorphic to Z3 and Z3 is a symbol group. 18 mod 0, which contains only 2 elements, so it is isomorphic to Z2. So all quotient factors or factor groups are symbol groups. So the 0 contained in the cyclic subgroup generated by 18 contained in the cyclic subgroup generated by 6, which is contained in the cyclic subgroup generated by 2, which is contained in Z36, is a composition series because each one is, because in fact this one is a normal series, so it is a subnormal series. That means each Gi is contained in Gi plus 1 and Gi is normal in Gi plus 1 and Gi plus 1 mod Gi is a symbol group. So this is a composition series. Now we can see something which is not a composition series. Following is an example of a series which is not a composition series. So consider the series 0 contained in 12, the cyclic group generated by 12, which is contained in the cyclic group generated by 4, which is contained in Z24. So you can see that this one is definitely a subnormal series. In fact, it is a normal series because Z24 is a abelian group. And this is not a composition series because we find the composition factor groups. The cyclic subgroup generated by 12 mod 0 that contains 2 elements, so it is isomorphic to Z2. The cyclic subgroup generated by 4 contains 6 elements and the cyclic subgroup generated by 12 contains 2 elements, so the quotient group of cyclic group generated by 4 mod with the cyclic subgroup generated by 12 contains 3 elements, so it is isomorphic to Z3. But Z24 contains 24 elements and the cyclic subgroup generated by 4 contains 6 elements. So in all, the quotient group contains 4 elements and we can show that that quotient factor group is isomorphic to Z4. But we know that Z4 is not a symbol group because it has a proper subgroup of order 2. because it's a cyclic subgroup. And you know that for each divisor D of n, G has a subgroup of unique subgroup of order D, because 2 divides 4. Z4 has a unique subgroup of order 2. So Z4 is not a simple group. So therefore 0 contained in the subgroup generated by 12 contained in 4, the cyclic subgroup generated by 4, which is contained in Z24, is not a composition series of Z24. But we can see another example which is useful for us in the later stage. When n is greater than or equal to 5, Sn has the following composition series, because the identity, that means the subgroup which contains only the identity permutation, which is contained in An, which is contained in Sn. In the last session, we have seen that A5 is simple. So in fact, by the same argument, we can prove that An is also simple if n is greater than or equal to 5. So An is a simple, and An mod identity is isomorphic to An, which is simple, and Sn mod An, which contains only 2 elements, so it is isomorphic to Z2, and Z2 is also simple. Therefore the factor groups are simple, and the An is a normal subgroup of Sn because the index of An in Sn is equal to 2, so An is normal in Sn, identity is definitely is normal in An. So therefore identity contained in An is contained in Sn is a composition series. Now we'll see what are the composition series of Z6. Now what are the subgroups of Z6? We know that if G is a cyclic group of order n and D is a divisor of n, then G has a unique cyclic subgroup of order D. So here you can see that 2 is a divisor of 6 and 3 is a divisor of 6. Therefore, Z6 has a unique subgroup of order 2 and a unique subgroup of order 3. That means that there are only 2 proper subgroups of Z6, namely the cyclic group generated by 2, which is of order 3, and the cyclic subgroup which is generated by 3, which is of order 2. And there is no intersection, the intersection which contains only identity element, because the cyclic subgroup generated by 2 is, the set is 0, 2 and 4, and the cyclic subgroup generated by 3 contains 2 elements, namely 0 and 3. So there is no common element other than identity element. So we have a lattice diagram for this. Namely, you can see that 0 is contained in the cyclic subgroup generated by 3, which is contained in Z6. And 0 contained in cyclic subgroup generated by 2, and which is contained in Z6. So you can have only 2 series of subgroups of Z6, namely 0 contained in the cyclic subgroup generated by 2, which is contained in Z6, and 0 contained in the cyclic subgroup generated by 3, which is contained in Z6. So since Z6 is abelian, these series are normal series in fact. So it is a subnormal series also. And what about the factor groups? The factor groups in the first series, that means Z6 mod with the cyclic subgroup generated by 2, which contains, the quotient group contains only 2 elements, so it is isomorphic to Z2. And 2 mod with 0 that contains 3 elements, so it is isomorphic to Z3. And in this case, Z6 mod with 3, which contains 3 elements, so it is isomorphic to Z3, and cyclic group generated by 3 mod 0, which contains 2 elements, so it is isomorphic to Z2. And Z2 and Z3 are simple. Therefore, all these factors are, the factor groups are simple groups. Therefore, both the series are composition series of Z6, and these are the only 2 composition series of Z6. That's all. In the next session, we discuss about more on composition series of groups. That means some properties, some more examples of composition series of group. Thank you.